So, we will move on from linear regression, linear methods for regression to linear methods for classification. Okay. And right, so far we have been looking at linear methods for regression, but I did tell you that you could do quote unquote non-linear regression also by doing appropriate basis transformations. So, what do I mean by linear methods for classification? Linear regression you can understand, right. So, the response is going to be a linear function of the inputs, right. So, what do I mean by linear classification?
The response is almost the same, but you decide a threshold above and below which you classify them as one.
So, when I am going to separate the positive classes, or right, when I am going to separate two classes, the boundary of separation between the two classes will be linear. Okay. So, that is what I mean by linear classification. So, this boundary that I draw between two classes will be linear. So, you can think of, I mean we did look at an example in the first class where we had drawn quadratic surfaces and things like that, right. So, but instead of that we will assume that the classification surface or the separating hyperplane will be a, well, or the separating surface will be a hyperplane, right. So, there are two classes of approaches that we will look at for classification, for linear classification, and the first one is essentially on modeling a discriminant function, right. So, one rough way of thinking about it is to say that I am going to have a function for each class, right, and if the function for class I, the output for class I is higher than for all the other classes, I will classify the data point as belonging to class I, right. So, I am going to have some function, right. So, for each class I will have a function, right, and so depending on whichever is the highest I will output it to that. So, this is essentially the idea behind discriminant functions, right. So, I am going to have to figure out a way to learn this delta i's. Okay. So, suppose let us just keep it simple, think of a 2 class problem. Okay. You had a question? Okay. So, think of a 2 class problem, and I have delta 1 and delta 2, right. So, where will be my separating hyperplane? Wherever delta 1 equal to delta 2, right. So, when delta 1 is greater than delta 2 it is class 1, when delta 2 is greater than delta 1 it is class 2, right. Wherever they are equal it will be this boundary, right. So, this will essentially be okay. So, if I need this to be a linear surface, right. So, what condition should delta 1 delta 2 satisfy? Should they be linear? Not necessarily, but okay, that is a sufficient condition. If they are linear, yeah, the surface will be linear. So, what else can they be? Huh? They can be non-linear as long as I have some kind of a monotone transformation of them which will become linear. Okay. So, we will see examples of this. We will actually look at discriminant functions, okay, or we will yeah. So, we will look at assumptions which will appear to be we are doing something non-linear, heavily non-linear, but at the end of the day you will find that the surface will be linear, okay, this separating surface will be linear. So, we will look at that as we go along, right. So, the few approaches that we look in this class are essentially linear regression, right. You could do linear regression and try to treat that as as your discriminant function. Right. For each class you could do, we talked about this in the very first class, right, or the second class, yeah. So where you could do linear regression on an indicator variable, so that will give you a discriminant function, or you could do logistic regression, or you could do linear discriminant analysis, which is like principal component regression, but taking into account the class labels. You will think of deriving directions and which you will be doing the classification. Okay. So look at the three of those. The second class of methods which we will come to is directly modular hyperplane. Okay. So it is related to this in some sense, right. So if I give you the discriminant functions, so I can always recover the hyperplane, but here instead of trying to do a class wise discriminant function, we will directly try to model a hyperplane. Okay. So this is the second class of problems. So we will look at one classic approach for doing that, which is the perceptron, right, and also talk about some more recent well founded ways of doing that, which essentially looking at the question of what an optimal hyperplane is, right, and trying to solve for it directly. Okay. So these are the two approaches we look at, right. So this basically just setting things up. So people remember the basic setup for classification, right. So I am going to assume that I have some space G which has k classes, right. So I will, for convenience, I will index them as 1 to k, right. X is going to come from RP as before, right, and my output is going to come from this space G. Okay, so that is our setup, and so if there are k classes, I am going to have k indicator variables, right. Now remember we talked about 1 of k encoding. So one of these k indicator variables will be 1 for any input, right, depending on what class that data point belongs to. Right. When this is assuming that my X has okay. So assuming I have augmented ones, so my beta hat is equal to X transpose X inverse X transpose Y. That is linear regression for you, right. So I can do just do linear regression on my response matrix. So beta is capitalized here because it is also a matrix, right. So one, so this is capital beta, if you are wondering what that is, right. You have one column for each of the classes, right. So for each class I have a set of beta. So I can produce a vector of outputs f, right, given an input x by essentially taking the product with the betas, right, that gives me a vector of outputs f, and and finally class label that I assign to the data point is argmax of the f's, right. So, I am going to get a vector of f's, one for each class, right, and the one that I assign finally is the one that gives me the maximum output. Okay. So, I have not done any complex math here at all. So, only bit of math here we already saw in the very first linear regression fitting. Okay.
What is the 1x thing with the
Yeah, because I wanted to add that I want to make it a p plus 1 thing, right. So, x is the input data point, I add a 1 to the front of it to for the bias. Okay. So, what does it mean? What do these fk's fk of x mean? So, what do these fk of x mean?
When you test a new data point, if some fk attains maximum, then it belongs to the k.
No, that is fine. I mean, sir, any semantics you can associate with fk?
Linear regression of on yk variable.
Yeah. So, if you think about it, so whenever the input x is of some class, let us pick a particular class, let us call it j, right. Let us have a class, or even make it more concrete, class 3, okay. The input belongs to class 3. Whenever the input belongs to class 3, okay, y3 will be 1, right. In the training data, if you look at it, whenever the input belongs to class 3, right, y3 will be 1. So, if you think about it, if you look at the expected output that you should get for a particular x, okay, the expected output you should get for particular x is, okay, how many, what is the average number of times it is going to be 1. If I am going to see the x again and again and again, right, whenever that x belongs to class 3, the output will be 1. When the x does not belong to class 3, the output will be 0, right. I see many times I see x, okay. So, what is the output I expect? It is the average of the outputs, right. The prediction should be the average of the outputs. Does it make sense? So, I have many x, they are not different x's, they are the same x, okay. Many times I am getting x again and again. So, sometimes it is class 3, sometimes it is not, sometimes it is not, sometimes it is class 3, okay. So, if I take the average of all of these outputs, what am I getting? No, I mean the probability that x is class 3, right. So, if I take the average of those outputs, I am getting the probability that x is class 3, correct. And we know that when I am trying to do the linear regression, what I am trying to predict is the expected value, right. Ideally, I should be trying to predict the expected value of this, but since it is linear, we will not be able to get there. But what we are trying to do is trying to predict the probability of the class, right.
This function is not constrained. So like if you have two f of x and for one of them it's like from 5, the f of 1 of x is 5 and second is 1, then which one should we classify?
Well,
Like ideally your output should be 0 or 1.
that is the whole problem of using linear regression, and that is what I am coming to it, right. So, you can't really interpret these as probabilities because linear regression is not constrained, right. So, we will come to that in a minute, how to fix that in a minute. So, but this is one, I am working up to that, okay. So, telling you the interpretation of what you want to do is that it is a probability. So, ideally you would like to interpret this, right. Right. So, the expected value of yk given x, you would ideally like it to be the probability that the output is k given the input is x, right. So, this is ideally that is what you want, and so linear regression gives you hope of getting there, right. And people sometimes still use linear regression because it is easy to do and other things, we will have to think of other ways of getting to it, right. I will come to that in a minute. So, before that I just want to point out one other pitfall of using linear regression for classification, right. But is it clear? Any questions?
Beta will remain the beta formula what you have written is same.
Yeah, this is same. This is
Beta what you have written the formula for the beta that is same for the linear regression.
that is linear regression.
But y is qualitative, right?
Sorry.
But the y is not the real numbers.
Why I have encoded it as 0 or 1, that is what we said, right. So, remember the indicator variable thing, so it is either 0 or 1, right.
Still the linear regression will hold.
Okay, what do you mean by hold, right. Still linear regression will work, right. So, I can do linear regression. So, I mean just as a method of using it, right, you can see how it is going to work, right. I am going to do linear regression. Give me a minute. Huh?
What the beta means.
What it means is, we ideally like it to mean this, it is not going to mean that. Okay, I will just hold on, I will do this example and then you can come back and ask me this question. Okay. Okay. So, I am going to assume there is a single input direction, right. So, let us say that so, let us say that there are data points here that belong to one class, okay, data points here that belong to another class, right. So, if you think about it, let us say this is encoded by pink, right. So, the training data, right, will look like this, right, and 0 elsewhere for pink, right. The training data for blue will look like this, and 0 elsewhere, right. So, now if I try to fit a straight line to this, so what do you think will happen? So, I will get a line that goes like that, right, I will probably get a line that goes like that, right. So, this is essentially what your outputs will look like, right. So, directly trying to interpret these as probabilities is not a good idea obviously, right, but you can see that wherever this is greater than this, okay, that should probably belong to class blue, wherever it is pink is greater than blue, it should belong to class pink, right. So, at least this much you can conclude from the output of the linear regression. So, that is essentially how you would interpret the output. So, whenever one output is greater than the other or greater than all the others, you will assume that it is the correct class. Directly interpreting that as probabilities is a problem. So, this is what you would like to do, this is what I said, right, but you do not want to do this. Okay. Having said this, let us see how visible this color is. Suppose I have a third class, okay, that is sitting in the middle like this, okay. So, the outputs for this will be somewhere there, right. Now, if I try to fit a straight line for this, what is going to happen? Right. Remember, the rest of the points are all sitting here, right. There are a bunch of zeros here, a bunch of zeros here, right, and a bunch of ones there. So, if I try to do linear regression on this, so I am going to get a line like that. Okay, what is the problem with that? Blue and pink completely dominated. There is no part in the input space where brown, there is no part in the input space where brown actually dominates, right. The output of brown never dominates anywhere.
So that line is actually the output from that dimension that
yeah. So this will be right. So this is essentially what your F1, F2, F3 will be. So it turns out that for class 2 you will never output any input point as class 2. Okay. So this problem is called masking. Okay. So this is one thing which you have to be aware of while you are doing linear regression for making your predictions. Okay. Is there any way to get over masking? Can you think of anything?
Probably regress on pairs.
Close. So instead of looking at pairs, you just look at higher order basis transformations, right? Instead of regressing on x, right? That's what we did here, right? So instead of regressing on x, if I regress on x squared, okay, I am going to get different outputs, right? Should I? Okay, good attempt, but next time actual English, not just coughing. Right. So if I am going to do that, essentially I am going to get curves that look like that. But the interesting curve is this guy. How is this brown curve going to look like? Right. So these are the crossover points. Right. So anything to this side will be blue, anything to that side will be pink, and anything in between will be brown. Right. You can see it.
Sir, which region, sir? Is that full side region?
Okay. So, but remember the input space is just on this line. Okay. So here this is the output, whatever is going up is the output. So the input is only on this line. Okay, it's just a single dimensional input. So it's no region per se, it's only a line segment here. So in this part of the input space it will be blue, this part it will be brown, in this part it will be pink. Right. It's almost ideal, except there is a small here. That's drawing error. Okay. So you can choose appropriate data points such that you can actually with the quadratic transformation, if you regress on x squared, you can recover the actual boundaries. Okay. So the rule of thumb is, if you have k classes in your input data, okay, you need at least k minus 1 basis transformation. So in fact with a lot of work you can show that even with x squared regression you will have masking if you have 4 classes. So in 4 classes you have to regress on the cubic transformation. Okay. So then you can still get away with it, right. So